Now here, since we are having two linear inequalities, so we need to find out the common feasible region graphically to solve this problem. I told you when you're finding the feasible region, you have to take x and y as 0, 0. So if you take x and y as 0, we get 0 less than or equal to 60, which is a true statement. So when this is equal to 0, so the region behind this will be less than or equal to inequality. When you say greater than 0, you should take a region which falls after 0 towards the x-axis. Everyone, a warm welcome to one and all. This is your Shruti ma'am, Vidhyaashram School of Excellence, Mysore. In today's session, we will learn to solve the simultaneous linear inequalities with the graphical method, which is studied under the linear programming problem. So in this session, we are going to study how we mathematically formulate linear programming problem and find the solution with the help of graphical method. So first, let us take an example here. Let us study how we mathematically formalize the linear programming problem. Now, let x be the number of tables and y be the number of chairs that a dealer buys. So when he buys it, obviously x and y must be non-negative. So mathematically, when we say the number of tables, it has to be greater than or equal to 0 and y has to be greater than or equal to 0. Now he needs to take a constraint of maximum amount. So to buy the chairs as well as the table, the maximum amount he can invest is rupees 50,000, and the storage constraint, that is, if he has to buy those things and keep it inside his shop, then he can store the number of items of maximum 60. So here we have two constraints. One is the constraint which is related to the investment and the constraint which is related to the storage. So when he takes the number of amount or the investment, the maximum he can investment is 50,000 and maximum number he can store the number of items is 60. So here what happens? So it is mathematically stated in such a way that the investment constraints of 2500x plus 500y less than or equal to 50,000 and 5x plus y less than or equal to 100 and x plus y less than or equal to 60. So this is the storage constraint. So let the cost of one table is 250 and the chair be 75 rupees. The dealer wants to invest in such a way so as to maximize his profit. Say z, which stated as a functions of x and y, is given by z is equal to 250x plus 75y. So this is, we have the following constraints for the given problem here. So one is in the investment constraints and one is in the storage constraints here. So apart from that, he needs to profit. He needs to maximize his profit by selling a chair as well as the table for 75 rupees and 250 rupees respectively. So what number of chairs and what number of tables he has to sell it so that he'll get the maximum profit apart from his investment. That is given by the linear objective function. We call it as linear because we can see here the equation is in the linear form. The degree of x and y variable is 1. So we call it as a linear function and that is denoted by z. So the cost of one table is 250. So x table is 250x. Cost of one chair is 75. So y chair is 75y. So how many chairs as well as tables he has to sell so that he has to maximize his profit. And this problem can be mathematically stated in this form. So it is now reduced to in this form. So maximize z is equal to 250x plus 75y subject to the constraint 5x plus y less than or equal to 100, x plus y less than or equal to 60, x, y greater than or equal to 0. Now here we have to maximize the linear function z subject to the constraints determined by a set of linear inequalities. Since we use the word maximum and minimum, the equations are not actually in equation form. It is not given in the form of equality. So it is given in the form of an inequality. So when we say the maximum number of storage constraint in 60, it is obviously less than or equal to 60, not more than or equal to 60. When we use the word minimum, then it will be obviously greater than or equal to 60. So here the storage constraint maximum he can store is 60. So it has to be x plus y, including tables and chair, it has to be 60. So thus we have to maximize a linear function. So this is called as a linear function subject to certain constraints, and these are denoted by the linear inequalities with the variables x and y here, which are non-negative again, which are non-negative. So such problems are called as linear programming problems. Now let us see a few definitions related to the linear programming problem. The first one is objective function. So a function z which is in the form of ax plus by, where a and b are constant, where the function is maximized or minimized, or the function where we will find the value of maximum or minimum is said to be the objective function. The next thing is constraints. Constraints are the condition related to the objective function, or mathematically we can say the linear inequalities or equations or restrictions on the variables of linear programming problem are called as constraints. The next thing is linear programming problem, a problem which seeks to maximize or minimize a linear function. So here we have a two variables x and y. So say of two variables x and y subject to certain constraints as determined by a set of linear inequalities is called as linear programming problem. Now let us find the solution of these linear programming problem by graphical method. So it's a very important question for your examination also. So you have one graphical solution and a linear programming problem. Now graphical method of solving linear programming problems. So I have taken the example of the previous one. So what is the question here? Maximize z is equal to 250x plus 75y subject to constraint 5x plus y less than or equal to 100, x plus y less than or equal to 60, x greater than or equal to 0, y greater than or equal to 0. Graphically, x greater than or equal to 0, y greater than or equal to 0 means it always represents the first quadrant, because here x is always greater than 0, here it is x axis and here it is y axis. So here x is greater than or equal to 0 and y is greater than or equal to 0 means the solution lies only in the first quadrant. So we have already learned solving linear inequalities graphically in class 11, where you have learned the feasible solution also. Now here, since we are having two linear inequalities, so we need to find out the common feasible region graphically to solve this problem. The next thing is we have two set of linear inequalities given. So there may be more than two also, but for this problem we have two set of linear inequalities. To these set of linear inequalities, we need to draw a straight line taking equality in the graph. For instance, we have 5x plus y equals to 100. So we are not considering less than or equal to 100. To draw a line, we take the equality sign here. For this also, we will take x plus y equal to 60. We will find the solution and we'll draw this. So let's take this in the form of x comma y. If we take x as 0, then y is 100. If you take y as 0, then this is 20. And similarly, if you take the values of x and y here, if x is 0, y is 60. If y is 0, x is 60. So the points here is 0, 100, 20, 0. And here we have 0, 60 and 60, 0. So once you get the solution for the given lines, we are going to draw lines for this. For instance, two lines which represents the equation here. Next, to find the feasible region, we will consider the region for the given set of inequalities. Now, if I plot the solution here and if I draw it on the graph, then I'll get the solution in this form. So we have already learned how to find out the feasible region for the given set of linear inequalities. Now let me explain this graph now. So we have xx dash and yy dash here. So I have taken the coordinates of y from 0 to 100 and coordinate of x as 0 to 70. Because the maximum value is 0, 100 and 20, 0. Let us plot this 0, 100, 20, 0. Now we have here 0, 100, 20, 0. So once we plot these points, we will draw the line and write the equation of the line which represents the line. Next, we have 0, 60, 60, 0. So I'll mark the point 0, 60, 60, 0. Then again I'll draw the line x plus y is equal to 60. Now the shaded region here represents the solution region, but how to find out the solution region? So we have the linear equalities 5x plus y less than or equal to 100. And the next thing is we have x plus y less than or equal to 60. So to find the feasible region, let us take x comma y as 0. Once we take x comma y as 0, put it as 0 comma 0. So for how many inequalities? You need to take the value x comma y as 0 comma 0. If you place x as 0 and y as 0, we get the inequality 0 less than or equal to 100, and this is a true statement. So we know that this line represents the line 5x plus y less than or equal to 100, and 0 less than or equal to 100 is a true statement, which means this is a solution for the given set of inequalities. That means the region which contains 0. So once we draw a line here, the entire region is divided into two sections. So one is after the line and before the line. So here we are getting it as a true statement. Hence, the region which contains 0 will form as the solution for the given set of line. So the solution behind this will form as the feasible region for the given line. For the next line, now let us take 0 comma 0, we get 0 less than or equal to 60, which means it's a true statement. Again, the region containing 0 will fall as the solution for the line x plus y is equal to 60. So therefore here, this will become or will act as a solution for the given line. The line below, the region below the line will act as a solution. Now we need to find the common region which satisfies both the condition. So we can clearly see here, the region which is shaded as blue here will fall as the solution region for the given set of lines here. And we know clearly that x is greater than 0 and y is greater than 0. So we need to shade only the region which contains in the first quadrant. So therefore, the region here will form as the solution region as a given set of linear inequalities. Now, we need to draw this, then we need to find out the solution. So this is half of the linear programming problem solution. Now, how to find the maximum for the given linear objective function? The next thing is, once you draw a feasible region as well as the set of line, once you get the region here, you need to mark the corner points here. So these are the corner points. So when we say it is a bounded region, it is clearly bounded. Bounded means it is bounded by the boundaries here. So it is clearly a bounded region. So for a bounded region, you will always have a corner points. So you need to mark all these corner points here. So here the corner points, I have named it as O, which is 0, 0, A 20, 0, B 10, 50, and C 0, 60. So once you plot this, you can find the values inside the graph here. So it is clearly, we can see it is 10, 50. And the rest of the points is already written on the graph. Once you get the corner points, so you are going to use a corner point table here. So here in this corner point table, once column, you will write all the corner points, and on the other column, you will write the objective function where you will find the solution at each corner points. Now, for 0, 0, if you substitute x as 0 and y as 0 here, z will become 0. And at A 20, 0, 250 into 20 plus 75 into 0, you will get the value as 5000. Similarly, for B, you need to put x as 10, y as 50, and for C, put x as 0 and y as 60 and find the value of z. Now, clearly from the corner point table, we can recognize the maximum value. So, once you get the maximum value, you can use it as capital M. If you want to find out the minimum value, you can use the symbol small m. Now, my aim is to find the maximum value of this objective function here. So, I have got the maximum value at the corner point 10, 50. So, we always get the maximum value of the function at the corner points for the bounded region. So, therefore, we can conclude the statement here. The maximum value is 6250 at the point B I have used, so 10, 50. So this will be the maximum value for the given linear programming problem. So this is how we are going to find out the maximum or minimum value of an objective function with the constraints, with the variables, which is called as linear programming problem, and this is the graphical method of solving linear programming problem. Now let's take few more examples. Now before that, let us study few definitions here. Feasible region. So feasible region means, so for this graph, I told you the solution region is nothing but the feasible region. So since we have two linear inequalities here, that means we will draw two straight lines. We need to find the common region where it will satisfy both the conditions of the linear inequalities. Hence here, this solution region which is shaded in blue will act as a feasible region. So which means here you take any points on the feasible region or on the boundary of the feasible region depending upon the slack or strict inequalities. So every point inside this region will act as the solution for the given set of linear inequalities. But remember, we always get the maximum or minimum value only at the corner points. So feasible region means the common region determined by all the constraints including non-negative constraints. So non-negative constraint means x greater than or equal to 0, y greater than or equal to 0 of a linear programming problem is called feasible region or solution region of the given problem. Next, feasible solution. Points within and on the boundary of the feasible region represents feasible solution of the constraints. Next, infeasible solution. Any point outside the feasible region is called an infeasible solution. So we have a feasible region. So any points inside the feasible region or on the boundary is called as feasible. Other than that, any point outside the region are called as infeasible region. Next, we have optimal solution or feasible solution. So optimal solution is the maximum value or minimum value of z. So which means any point in the feasible region that gives the optimal value. Optimal value is nothing but the maximum or minimum value, and optimal solution means the point at which we are getting the maximum or minimum value. So that is called as an objective function, which is called as an optimal solution. So the point where you will find the optimal value, that means the maximum or minimum value of an objective function, is nothing but the optimal solution. So for the previous example, the point B is called as the optimal solution and 6500 will act as an optimal value. For the previous solution, the point B acts as an optimal solution and 6250 will act as an optimal value. Now let's find the graphical solution for the linear programming problem. So here we have minimize and maximize z is equal to 3x plus 9y subject to the constraint x plus 3y less than or equal to 60, x plus y greater than or equal to 10, x less than or equal to y, and the non-negative constraint. So again, it clearly indicates the solution should lie only in the first quadrant. So let us solve these linear inequalities. We have three set of linear inequalities, x plus 3y. Let's take it as 60 while graphing this. Next, we'll take x plus y equals 10. Next, we'll take x is equal to y. Let's find the solution here. Now, I'll use x as 0. We'll get 3y is equal to 60. So, y will become 20. So, 0, 20 is the point. And here I'll take y as 0, then I'll get 60. So 60, 0. So to draw this line, we are supposed to use the point 0, 20 and 60, 0. So by taking x and y as 0, we can easily find out the other variable. So I always prefer taking x as 0 and y as 0. The next thing is we have x plus y equals 10. So here we take x, y. If you take x as 0, y will take it as 10. If you take y as 0, then x is 10. So the points for this line is 0, 10 and 10, 0. And here we have x is equal to y. So when I take x is equal to y here, if we put x as 0, then y is also 0. Again, I can't put y as 0 because the point is already origin 0, 0. So we need to take some other solution here. Let me take x as 10, then y is also 10. So the point is 10, 10. So once I plot all this inside the graph and recognize the feasible solution, so the graph looks like this. So we have all the three straight lines along with the feasible solution. First, let us find the feasible region, how to recognize this. So first equation of the line for x plus 3y is equal to 60. The point is 0, 20 and 60, 0. So here is the point 0, 20 and 60, 0. We will draw a straight line and then write the equation of the line. The next point is for x plus y is equal to 10, which is 0, 10 and 10, 0. Again, we'll draw a line and we'll write the equation of the line. The next thing is the line which is x is equal to y. So x is equal to y, we have 0, 0 here and I have taken the point 10, 10. So we will draw this line. So which is this line? X is equal to y. Now to find the feasible solution. So we have this line x plus 3y less than or equal to 60. I told you when you're finding the feasible region, you have to take x and y as 0, 0. So if you take x and y as 0, we get 0 less than or equal to 60, which is a true statement. Obviously, when you consider this region, the region containing 0 will act as a solution for the given inequality here. So this will be the solution region for this line. Next thing is we have x plus y. We have x plus y greater than or equal to 10. So we have drawn a line x plus y greater than or equal to 10. So put 0 here. Then 0 greater than or equal to 10 is a false statement. Which means for the given line, the solution region is where which does not contain 0. So if you take this region, it contains 0. Obviously for this line, the region above the line will act as a feasible solution. The last one is we have x less than or equal to y. So 0 less than or equal to 0 is a true statement and obviously less than or equal to 0. So this is equal to 0. When I say less than or equal to 0, this region will act as a solution for the given line x less than or equal to y. Now which is the region which satisfies all the condition? We can clearly see this quadrilateral. So the quadrilateral here, which is represented as A, B, C, D, forms as a solution region or a feasible region for these inequalities. So once you find the feasible region here, so you can clearly mark all the corner points here. So we have already have the corner points on the y-axis when we are plotting the inequalities here. The first thing is 0, 10. The second is 0, 20. The third and fourth we can find using graph. So clearly you can see this is 5, 5 and this is 15, 15. So this is 15, 15. So C 15, 15, D 0, 20, A 0, 10 and B 5, 5 are the corner points of this feasible region. Now once you find all the corner points, you are supposed to put this in the corner point table to solve the objective function z is equal to 3x plus 9y. Now since we have got all the corner points here, we'll put it in the corner points. We will take the values of respective xy. So here we have 0, 10, which we get 90. When you put 5, 5, we get it as 60. When we get 15, 15, we get it as 180. When we get it as 0, 20, we get it as 180. Now we need to find both the maximum as well as the minimum value. Now clearly from the table, minimum value of z is 60. So we will write minimum value is 60 at B 5, 5. But we have the maximum value which is repeated at more than 2 points, which means from the graph you can see the maximum value will exist at C as well as D, which means a line segment which joins CD will act as the solution, or wherever the point on the line segment CD will give you the value as 180 itself. So when you find the solution repeats in more than at 2 corner points, that means the entire line segment which connects these 2 points will act as the solution, where you will get the maximum value as 180 degree. So here we have maximum M. So how to conclude this? Maximum value is 180 degree at the line segment joining the points C 15, 15 and D 0, 20. So this is how we will write the solution. So if you have a maximum value or minimum value repeats at more than 2 corner points, then you have to state the conclusion in such a way that the maximum value or the minimum value will be at the line segment joining the given points. Next thing, minimize z is equal to minus 3x plus 4y subject to the constraints x plus 2y less than or equal to 8, 3x plus 2y less than or equal to 12 and x greater than 0, y greater than 0. Again, the solution is only on the first quadrant. Now, once I plot these inequalities inside the graph looks like this. So, the first line, we have x plus 2y is equal to 8. So, 0, 4 and 8, 0 will be the solution of the line. So, using that, we can plot a straight line. And for the second line, 3x plus 2y is equal to 12. 0, 6 and 4, 0 will act as a solution. Now, to find out the solution here, so both inequalities we have less than or equal to. So, that means the area below the line represents the solution. So, and this will be the common region which satisfy both the inequalities. Now, since we got the feasible region, we will mark the corner points here O, A, B, C. From the graph, we can recognize what is this point, which is 2 on x-axis, 3 on y-axis. So, the point 2, 3 is the corner point B. So, next, once you get all the corner points here, we will put it in the corner point table and we will find the optimal solutions taking x and y value respectively. Now, O0, 0 gives z as 0, A4, 0 gives you minus 12, B2, 3 gives you 6. And C0, 4 gives you 16. Now, my question was to find the minimum value of Z. Now, clearly we can see minus 12 is less than 0. So, obviously, this will act as the minimum value. So, hence, how we will conclude this statement? We conclude is thus, the minimum value of Z is minus 12 at the point A4, 0. So, A4, 0 is the optimal solution and minus 12 is the optimal value. Next question we have. Minimize and maximize z is equal to x plus 2y subject to the constraints x plus 2y greater than or equal to 100, 2x minus y less than or equal to 0, 2x plus y less than or equal to 200 and x, y greater than or equal to 0. So, when we take x plus 2y greater than or equal to 0 as a solution and 2x minus y. So, 2x minus y can also be written in the form of 2x minus y is equal to 0. So, we get y is equal to 2x. So, when you are taking such kinds in x and y axis, if you take x as 0, then you will get y as 0. So, you have to take other than 0, 0. So, you need to take, for instance, x as 10, then y is equal to 20. So, for this line, you can use 0, 0 and 10, 20 as the points to draw the line. Now, this is, again, we will plot this inside the graph. Now, clearly, the graph of the linear inequalities looks like this. So, the first set of linear inequalities x plus 2y is equal to 100. So 0, 60, 100, 0 is the point. So we will draw a straight line. Now for the second line, we have 2x minus y is equal to 0. And the third line, we have 2x plus y is equal to 200. Once you plot all these inside the graph, considering the equation, we have x plus 2y greater than or equal to 0. For x plus 2y greater than or equal to 100, if you put x and y as 0, we get 0 greater than or equal to 100, which is a false statement. So this line represents the line x plus 2y is equal to 100. Obviously, the region which does not contain 0 should be the solution. So the region above the line will act as a solution for this line. Next, we have 2x minus y less than 0. Obviously, we have this as 2x minus y is equal to 0. The region behind this will act as a solution. Next, we have 2x plus y less than or equal to 100. And here we get 0 less than or equal to 200, which is a true statement. That means the region which contains 0 for this line. So this is the line 2x plus y is equal to 100. This region contains 0. So the solution region will be behind the line. So now the only region which satisfies all the three conditions is this quadrilateral. Once you get the quadrilateral, mark the corner points here. So again, it's a bounded region. So once you get the corner points using the graph, plot this in a corner point table and find the value of z. Now here in this question, I need to find both minimum value as the maximum value. Now clearly we can see here, the maximum value is at 400, but the minimum value is at the 2 points. So therefore, we will conclude the statement, the minimum value of z is 100 at the line joining the points a 0, 50 and b 20, 0, which means this entire line segment will act as the solution to find the minimum value of the given function. And the maximum value of z is 400 at the point 0, 200. Next question, minimize and maximize z is equal to 5x plus 10y, x plus 2y less than or equal to 120, x plus y less than or equal to 60, x minus 2y greater than or equal to 0, and again x greater than 0, y greater than 0, which means you need to take the solution only in the first quadrant. Now, let us assume that we have already drawn a line for this to find the feasible region by taking x and y as 0. So, 0 less than or equal to 120. It's a true statement. That means for this line, the region which contains 0 will act as a feasible solution. Here, 0 greater than or equal to 60, which is a false statement, which means the region which does not contain 0. So if you draw a graph like this, if this is a line which represents the line x plus y is equal to 60, we have two regions. One, a region which contains 0, 0, other region which does not contain 0, 0. If you get the true statement, you should take the region which contains 0. If you get the false statement, you should take the region which does not contain 0. Now, when I say this as x plus y is equal to 60, then this will be the feasible region for this inequality. Next, we have x minus 2y greater than 0. So, obviously, we get 0 greater than or equal to 0. So, for such kind of lines, this is a line which always passes through the origin. So, when this is equal to 0, so the region behind this will be less than or equal to inequality. When you say greater than 0, you should take a region which falls after 0 towards the x-axis. Now, once you plot all these inequalities inside the graph and when you recognize the feasible region, so for this linear inequalities, the graph looks like this. Now, once you find a feasible region, mark the corner points A, B, C, D. Recognize the point using the graph. So for C, you can clearly see it is 60 along x-axis and 30 along y-axis. Once you recognize the feasible region, mark the corner points and the rest of the points can be recognized using your graph sheet. So you can recognize x value as well as the y always. Always write in the form of x, y, not in the form of y, x. Do not confuse. The ordered pair should be always x and y second. Next, use the corner points in the corner point table and substitute the values of x, y respectively in z and find the solution. Now for this question, we have both minimize and maximize. So therefore, the minimum value of Z is 300 at point 60, 0 and the maximum value is 600 at the line segment joining B and C. So that means inside the graph, the line BC, the entire line segment BC will give you the maximum value of 600. Any point on the line segment will represent the solution or will represent the maximum value for the given linear objective function. Now until now we have discussed the solutions for the bounded region. So I said bounded means it is having the boundaries. Now let's take an example of an unbounded region and how to find out the solution whenever the graph is unbounded region. Now let's take few example. Minimize Z is equal to 3x plus 5y subject to constraint x plus 3y greater than or equal to 3, x plus y greater than or equal to 2 and x plus y greater than or equal to 0. So if you use this and plot on the graph and recognize the feasible region, clearly you can see it is greater than or equal to 3 and greater than or equal to 2. Now the graph looks like this when you take the values here. So this line represents x plus y greater than or equal to 2, which means the region is above the line. And for this line also the region is above the line. So the entire region on the x-axis will be the feasible region for this graph. Now once you find the corner points here also, you can see it is on the x-axis here and on the y-axis. So not anywhere else, because the entire x-axis will form as a solution. So there will be no other corner points other than these three. Now let us substitute inside the graph. Now let us substitute inside the corner point table. So we get the corner points like this and we'll get the solution like this. Now my aim is to minimize. So therefore you can clearly see 7 will be the minimum value for the given function. But for an unbounded region, we cannot recognize the minimum or the maximum value directly as we have did it in the bounded region. So what we are supposed to do now? Now recognize the minimum value and take the objective function. Now recognize the minimum value 7. So once you get the minimum value, you cannot conclude that 7 is the minimum value of Z at the given points. So in bounded region, it is not so easy to find out the maximum or minimum value as we did it in the bounded region. So now keep the Z value as 7 and now draw one more line taking 3x plus 5y less than or equal to 7. Since we are talking about the minimum, we need to find out the region which is 3x plus 5y less than or equal to 7. So let us plot this on the graph. So for this graph, once you draw a line 3x plus 5y less than 7, the graph contains one more line which is this 3x plus 5y less than 7. So this is the line which is 3x plus 5 less than 7. The region below the line will act as this feasible region for the line 3x plus 5y less than 7. Now you can clearly see the feasible region does not intersect with the region which is 3x plus 5y less than 7. When you find any point of this line intersecting with the region, then there is no maximum or minimum value for the given linear objective function. So you have to recognize whether the feasible region of the third constraint is intersecting with my feasible region. Now here in this diagram, we can clearly see nowhere they are intersecting to each other. So no point is common with the given set of equation, and this is strictly a strict inequality. So not even this point is intersecting with my feasible region. We know that for a strict inequality, we always draw a dotted line, which means the points on the line is not the solution. Only the points above or below the line will act as a solution. Now, since my solution is below the line and my feasible region is clearly above the two lines, they are not intersecting each other. So, clearly, we can conclude that 7 is the minimum value of the given objective function. If suppose the region intersects with each other, or the line intersects with the feasible region, or any point on the line or below or above the line will intersect with the feasible region, then conclude that there is no maximum or minimum value for the given objective function. But for this problem, we can clearly say that 7 is the minimum value of the z at the point B 3 by 2, 1 by 2. So we'll take one more example of an unbounded region. We have a question here, minimize z is equal to x plus 2y subject to constraints 2x plus y greater than or equal to 3, x plus 2y greater than or equal to 6, x comma y greater than or equal to 0. Solution region lies only in the first quadrant. So once you plot these lines, the graph looks like this. So since we have both the lines having an inequality greater than or equal to the given value, the line above the line, this x plus 2y is equal to 6 will be the common feasible region for both the lines. Now these two acts as the corner point here. So clearly once you find the value at 0, 3 or 6, 0, 6 will be the optimal value. Now once you get the corner points and the optimal value or the minimum value of 6, take the equation as x plus 2y less than 6. So we have the line x plus 2y is equal to 6. When I say less than 6, this is, when I say less than or equal to 6, this is the solution. So clearly we can see here, not even this region is intersecting with my feasible region because the solution clearly say x plus 2y is less than 6. So when I say less than 6, the points below the line will act as the solution for the given inequality. So nowhere one among the points are intersecting with the feasible region. So here also we can clearly say that 6 is the minimum value, or we can say the 6 is the minimum value of the given objective function. So, or the line segment joining AB, any point on the line segment joining AB will act as an optimal solution to get the optimal value 6 or to find the minimum value 6. Now for instance, if we get any other third line intersecting like this with my feasible region, then we can directly conclude there is no maximum or minimum value for the given linear programming problem. So in today's session, we have discussed how to formulate the linear programming problem, and we have found the feasible solution as well as found the maximum minimum value of a linear programming problem by graphical method. So when we say the application of linear programming problem, it is always to maximize profit with the minimum cost. It is always well-versed use wide of applications in economics, business, and in the field of commerce. I'll meet you in the next session with a new chapter. Until then, keep watching, keep learning, and keep exploring. Thank you.